So measuring center, there are two ways to measure the center of a distribution, the mean and the median. So we're gonna look at that. So the first is the mean, which is the arithmetic average. There is a symbol in stats that we use for the mean. It is an X bar over it. We're pretty creative as statisticians. We call this X bar. Okay, it represents the mean of a sample set of data. So how do we calculate the mean? Add up all the values and then divide it by the total. Okay, so here's the formula. We've got X bar equals X1 plus X2 plus ... X to the whatever, X sub n. And then we're going to divide by the total, which in this case would be n, to get the mean. Right? That's how grades work. Or if we write it in sigma notation. Sigma meaning what? The sum. I'm gonna add everything up, okay? All of the data points, and then divide by the total. Okay, so you don't really need to know these formulas, all right? But we put them there for the mathematical fluency, right? So that we can see where it's coming from. Example 1 says, how long do people spend traveling to work? The answer may depend on where they live. Here are the travel times in minutes for 15 workers in North Carolina, chosen at random by the Census Bureau. Calculate the mean amount of time spent traveling to work and graph the histogram using the calculator. Tell you what, we're gonna skip that for right now for the sake of time. Just go ahead and calculate the mean for me using your calculator. Okay, and so if you add up all the data points here, you should get 337. And we are going to divide that by 15. And so one way that you can, your TI Nspire is probably set to give you an exact answer. And so it may leave it as a freshman. What is that? Come on, Nerdhouse. It may leave it as an exact answer. Whew, it's early. You can put a dot right there by the 15 and it will give you a decimal answer. Or you can convert it fraction to decimal also. But probably the easiest thing is if you put 337 divided by 15 and then put a period after the 15, it will give you a decimal answer, which is, what's the mean? 22, we'll round it, okay, 22.5. Is there a value that looks like it might be an outlier? Maybe, right? At 60, some person has to travel an hour to work, right? This says remove that value and recalculate the mean and what happened to the mean. So look, we're gonna do 337 minus 60. And then we're going to divide that by 14, right? Because we removed one of them. And so 337 minus 60 divided by 14, we get 19.79, something like that. And so what happened to the mean when we removed the potential outlier there? The mean, it went down. So we say that the mean is considered to be not resistant because it is sensitive to the influence of extreme observations. Okay. And so the median is the middle value. We are going to arrange in order from smallest to largest. If n is odd, then the median is the center observation in the ordered list. If n is even, then the median is the average of the two center observations. So go ahead and put the data points in order and find the median for me. Can you do that? So what's the mean? Sorry, what is the median? Yes, what'd you get? 20? Is that what? Everybody, we agree with that? So the median of this is 20. Well, let's say if we change the largest data value of 60 to 80, what would happen to the mean? The mean would get larger, right? I'm increasing a data point, therefore it makes sense that the mean would become larger. The mean gets larger. Well, what would happen to the median if I did the same thing? Stays the same, right? It stays the same. So we would say that the median is, and what goes in the blank? The median is blank because it is not easily influenced by extreme observations. So the mean is not resistant because it is affected. The median is resistant. Okay, so let me show you how we use this, for example. Newhouse goes out to lunch with a couple of his friends and Jeff Bezos, the owner of Amazon. Together, we have an average net worth of like $14 billion. I didn't know if you knew this, but I got into teaching for the money and the fame. I'm independently wealthy, right? So our average net worth because of me? Well, no. The owner of Amazon, right, is extremely wealthy. Okay. And what would that do to the average of our little dinner party there? It would increase it dramatically. Okay. So for example, let me give you a very practical example. You go for a job interview. You don't need to ask what is the mean salary for this company, right? You need to ask what is the median salary for this company? Because the median is resistant to extreme observations. So if they say we have an average salary at this company of $100,000. Okay, well, what is the CEO making? And what are all these people in upper management making? That's going to pull the mean. That's going to pull the mean upwards, right? Does that make sense? Whereas the median is resistant. So if you're looking to buy a house in a certain neighborhood, for example, you need to check the median value of the houses in that neighborhood instead of the mean. Because if there's all these regular houses and then there's one mansion on the hill, right, that's worth a lot of money, the mean value of the mansion is going to increase that average dramatically. That makes sense? Okay, so this is kind of important, comparing the mean and the median. If the shape of the distribution is approximately symmetric, then the mean and the median are close to being the same. If the distribution is skewed to the right, the mean is pulled closer to the long tail, but the tail is at the upper values. So we would say the median is less than the mean. And if the distribution is skewed to the left, the mean is pulled closer to the long tail, but this time the lower value. So we would say the median is greater than the mean. So turn the page, and I think that will make sense when we look at the graphs. Okay, so look up here at the graphs. If we have a symmetrical distribution, okay, then the mean and the median are probably close to being the same at the center. However, if we have a distribution that is right skewed, that means there is some extreme observations on the right. It is going to pull the mean towards those extreme observations. Therefore, in a right skewed distribution, right skewed, the mean is going to be greater than the median. And the same thing works for a left skewed distribution. Okay, in a left skewed distribution, mean is going to be less than the median. Because, look up here for a second on this graph. Okay, in a left skewed distribution, I have extreme values over here on the left. And since the mean is pulled this way towards those extreme values, then it is going to be less than the median. Okay. Questions? Okay, well, we are going to look at some measures of spread. Looking back at the data from example 1, well, let's answer this question. Which measure of center would be more appropriate to represent the distribution of drive times, the mean or the median? So on this one, I said probably the median. Although there is not a lot of difference in this case. Not a lot of difference because what was the mean? 22.5, and the median was 20. Right, so there's not a whole lot of difference in those two things in this instance. Okay, so let's talk about measuring spread. 3 different things we are going to look at, all right? Range, IQR, and standard deviation. So the range is the difference between the smallest and the largest observations. And I'm going to put me a little note here. It is a single number. So it is mathematically incorrect to say the range is from 5 to 60. Okay, I understand what you mean, but that is mathematically incorrect. It's a number. Okay, it is the difference between the largest and the smallest. You can say that it varies from minimum to the maximum, or the spread is from the minimum to the maximum, but the range is a single number. Distributions can also be broken down by quartiles. Okay, so we have the first quartile, or Q1, it is larger than 1/4 or 25% of the observations. And Q2, or the median, is larger than 1/2 or 50% of the observations. And the third quartile, the upper quartile, Q3, it is larger than 3/4 or 75% of the observations. So how to calculate the quartiles? By hand. Again, we'll do this once and then we'll use our calculators. We are going to arrange in increasing order and locate the median. Q1 is going to be the median of observations whose position in the ordered list is to the left. And Q3 is the median of the observations in the list to the right of the overall median. And then we have the IQR. The IQR measures the range of the middle 50% of the data. It is the distance between Q3 and Q1. It measures the spread of the middle of the data. So IQR right here is always Q3 minus Q1. Okay, let's look again at the 15 workers' travel times arranged in increasing order. All right, I'll let you do this. Find the median and then Q1 and Q3 for me. And label them. The median, there's 15 total observations. So the median would be the middle one, which is this one. All right. The median is also called Q2. And so then if we look to the left, there's 1, 2, 3, 4, 5, 6, 7 data points. And so the median of that would be this one. And that is Q1. And same thing on the right side. There's also 7 data points. We're going to look at the median of that, which would be this one, 30. And that is going to be Q3. And so this says locate the median, Q1 and Q3 above. We did that. Then calculate and interpret the IQR. Okay, so IQR is going to be Q3 minus Q1. So in this case, that would be 30 minus 10. So the IQR in this case would be 20. And then it says to interpret the IQR. So we are going to say it is the range of the middle 50% of the data. And the next question says, are the quartiles in IQR resistant or non-resistant, and why? What do you think? Headed one, resistant or non-resistant?
I'd say it's resistant because like we're calculating medians depending on the number of values, not fixed values.
Okay. Put some numbers in. Let's say I change this to 100. Does the IQR change? No, it does not. Therefore, the IQR is resistant because it is not sensitive to extreme observations. Okay, so we're going to say the IQR is resistant. Do the quartiles change? No. Does the IQR change? No. Therefore, both of those are resistant. Okay, so the IQR is resistant because it is not affected by extreme observations. And that brings us to this. Okay, there is a mathematical way of calculating an outlier. Okay, it is given by this formula. So an outlier is a data point that is more than 1.5 IQR below Q1 or above Q3. So Q1 minus 1.5 IQR, anything lower than that is an outlier. Q3 plus 1.5 IQR, anything higher than that is considered an outlier. So do we have any outliers in our 15 workers travel times? All right, so Q1 is 10 minus 1.5. What was the IQR? We found it right here. It is 20. So I've got 10 minus, what's 1.5 times 20? 30, right? So I've got 10 minus 30, which gives me a negative number, which does not make sense in the context of this problem, because we are talking about commute times. So this is no outliers. And what about over here? Q3 is 30 plus 1.5 times the IQR, which is 20. That's going to give us 30 plus 30, which is 60. However, it must be higher than that. And our largest data point was 60. So we have no outliers in this one either. Anything greater than 60, like if it were 100, I changed it there, that would be an outlier, but otherwise, no. So we have what is called the 5-number summary. So the 5-number summary is the minimum, Q1, the median, Q3, and the maximum. So we found those by hand, right? We didn't do the max and the min, but we put them in order. So the minimum was 5. Q1 was 10. The median was 20. Q3 was 30. The maximum was 60. And so now what I want to do is show you how to use your calculator to calculate the 5-number summary. And we're also going to create a box plot using our calculator. Okay, so let's do that. So in the spreadsheet next to your data, highlight the cell that is next to the data. And I told you earlier, your new best stats friend is 1var stats. So we are going to run one variable stats on the data. So we go to menu. We go to statistics, stat calculations, and then option number 1, which is 1var stats. And then number of list, 1 is fine. But right here, you're going to click on the arrow and choose the name of the data that we want to run one var stats on, which was the times. And then we hit OK. So help out your neighbor there in case they got stuck. So looking up here, right, we have X bar, which is, what's X bar again? That's the mean. We have the sum of all of the data points, which was 337. We have the sum squared. We have the standard deviation, which we'll come back to. The number of data points was 15. That's n. Okay, and so look right here. We have the 5-number summary. We have the minimum is 5, Q1 is 10, the median is 20, Q3 is 30, the max is 60. And that we will come back to in the future, okay? So the test is all calculator, so we don't need to calculate the 5-number summary by hand, right? We can just put the data into our calculator and run one variable stats, and it will give us the 5-number summary and the mean and that type of thing. So what I want to do now is to make a box plot. And so there are some instructions about how to do that by hand in your notes, but let me show you how to use your calculator. So I am going to add a page. So from the spreadsheet, I'm going to go Control Doc, add data and statistics, which is option number 5. I want to click to add variable down here and then select the times, and it will give me a dot plot. That's the default plot. So if you put the cursor up above the dots and you go to menu, plot type, and then choose box plot, which is option number 2, it will give you a box plot. And so now what I want you to do is to take your cursor and move it over. Okay, so look up here at mine for now. Okay, so what do you notice? If I do this, that gives you the minimum, which is 5. And then this right here is Q1, which is 10. This line in the median, excuse me, this line in the middle is the median. This right here is Q3. And then out here we have the maximum, which is 60. And so this right here, the box, is the what? It is the interquartile range, or the IQR, right? The middle 50% of the data. And then it's sometimes called a box and whisker plot, okay? This line extended out here is it goes from Q1 to the minimum, and then this line from on the right side goes from Q3 to the maximum. So a couple of things. Look at the box plot, and what is the shape of this distribution? Based on the box plot, can we determine the shape? We can, okay. I would say it's right skewed. How do we know that it is right skewed? Well, look at this line. Since this line is much wider than this line because of the maximum here at 60, we can say that this distribution is right skewed. If it were shorter, let's say it ended like right there, then I would say that it is roughly symmetrical, right? And the last thing, if there are any outliers, we won't look at this right now, but if there were any outliers, it would be denoted by some type of symbol, like an asterisk out here, okay? But there's not any of those. And so maybe at another time, we'll look at a distribution with an outlier, but we calculated that by hand, right? And saw that there were no outliers. But in the calculator, it would appear as a dot out there as an outlier. Okay, so let's go back to the notes here and let's graph the box plot. So I am going to do this by hand. We're going to scale this. Label 5, 10, 20, 30, 35, 40. And this is commute times. And minutes. Label your graphs, right? Scale them. And when we are drawing the box plots, I think I usually start with the IQR. So I'm going to draw a line here at 10, and then a line at 30, and draw my rectangle. That's the middle 50%. The median is there at 20. And I am going to extend a line from Q1 to the minimum, and then extend another line from Q3 to the maximum. And so what percentage of the data is contained in this line? Well, that would be the upper 25%, because it goes from Q3 to the maximum. That makes sense? All right. Well, one last thing here, and I will finish this up tomorrow, but this is a pretty important concept that we will use the rest of the year. So I want to see if I can explain it to you in a way that makes sense. Okay. We have what is called the standard deviation. And this, as I said, this is an extremely important concept in stats. The standard deviation measures the typical distance of the values in a distribution from the mean. The symbol for the standard deviation for a sample set of data is S sub x. And then we have what is called the variance. The variance of a set of observations is the average of the squares of the deviations of the observations from their mean. Okay, the variance is the standard deviation squared. And it is denoted by S sub x squared. And this is an extremely important concept in stats. So let me see if I can explain it to you. And then if we have time, we'll kind of go through some of the calculations. And I will show you mathematically how the standard deviation is calculated. But again, we won't need to do that, because if you go back to 1var stats, the standard deviation is in that list of things that 1var stats gives you. Okay, so let's say hypothetically speaking, I give a test in stats and everybody in the class makes an 80 on the test. So what is the class average? 80. However, the standard deviation for that set would be 0. And the reason that it's 0 is because all of the data points are equal to the mean. There's no variation from the mean. Does that make sense? And so the class average would be 80. However, the standard deviation is 0 because everybody in the class made an 80, and that is equal to the mean. That makes sense? Okay, well, in my other class, let's say that half of the class makes a 100 on the test, and the other half of the class makes a 60 on the test. So what is the class average? It's also 80, right? Because half made 60, half made 100, and so the average of that would be 80. However, the standard deviation is not 0. In fact, it's much greater than that. Does that make sense? Because half of the class made a 60, which is far from 80, and half of the class made a 100, which is also, relatively speaking, far from 80. And so what standard deviation is, I need you to remember this example, okay? Standard deviation measures the typical distance of the values from the mean. If all we have is the mean, and I'm looking at how both classes did in my class, on the one hand, everybody in the class made a low B. And in the other class, half of the class did great. They made a 100, and the other half of the class failed. And so those are two distinct and different distributions if we are just looking at the mean. Does that make sense? And so the average can be a little bit misleading. And so what standard deviation does is it tells us how far, on average, the data is from the mean. Because this helps us, well, it helps us the rest of the year do some things. But does that make sense? Okay, so let's look at this. And I'll probably end with this right here. I'm going to give you the mathematical formulas for the standard deviation, but I don't think I'll have time to go through this example here. But let me give you that. But let me ask you this. It says, are variance and standard deviation resistant or non-resistant? And why? I want you to think about that question for just a second, okay? So here's the formula for the variance. Okay, so don't be intimidated by this formula. All right. So this, what this formula does, it takes a data point, it subtracts the mean, x bar, then it squares it. It squares it because it's the variance, and the variance is the standard deviation squared. Then it adds all those up with the sum, and then we're going to divide by the total number of data points minus 1. Okay, the standard deviation is the square root of the variance. So it's the exact same formula, except we are going to take the square roots of everything. So it would be 1 over n minus 1, sum x of I minus x bar squared. But let's go back to my question there. Is standard deviation and variance resistant or non-resistant? Are they affected by extreme observations? Why would you say they are?
All numbers which would include outliers, and the outliers would influence the number.
Okay, so let's go back to the first example there. Or let's go back to this example. If I change the max to 150, does that change how far spread out the data is from the mean? Yes, it does, okay? Therefore, they are affected by outliers, therefore we would say that the standard deviation and variance are, what's the word? Not resistant. Okay, we are going to stop